Hi, I'm Amanda Lawter, and today I will be presenting sediment interactions with layered bismuth materials, implications for subsurface contaminant remediation. Today I will be talking about two bismuth-based materials. Bismuth oxyhydroxide, or BOH, is synthesized in the lab by a soluble thermal treatment of bismuth nitrate and urea in ethylene glycol, producing a homogeneous, mostly amorphous material. You can see two SEM images of BOH on the left. Bismuth subnitrate, or BSN, is commercially available and is more crystalline than the BOH. It is prepared through hydrolysis of an acidic solution of bismuth nitrate through the addition of an alkali. In general, BOH is more open and disordered but becomes more crystalline after contact with solution. The BOH XRD pattern prior to contact with any solution is shown here in black, and the general structure is shown here with bismuth in purple and oxygen in red. BSN is comprised of tightly packed bismuth clusters charge balanced by nitrate. It's ordered into large crystalline domains. The BSN XRD pattern is shown in red, and the structure is shown here with bismuth in purple, oxygen in red, and nitrate in gray. Also shown here are the most prevalent forms the BOH and BSN take after contact with solution, including bismuclite, bismutite, and bismuth hydroxynitrate. In most tests we've conducted over time, the BOH mostly forms bismutite, while BSN forms bismuth hydroxynitrate and/or bismutite in most cases, although many other bismuth-based structures have been identified in post-experiment XRDs of the bismuth material. Our team has been testing these two bismuth materials in a variety of solutions with a variety of contaminant concentrations over the past few years. The tests represented here include variable background solutions, including synthetic groundwater or synthetic perched water, various solid to solution ratios, and different concentrations and mixtures of contaminants. While they're not all directly comparable, in general the tests have shown that BOH and BSN have been able to remove more than 90% of aqueous uranium, technetium, chromium, and iodine in a variety of geochemical conditions. This table shows tests using BOH or BSN in either synthetic groundwater with individual contaminants, synthetic groundwater with co-contaminants, so all of the contaminants mixed together, or synthetic perched water. With combined contaminants, removal of uranium and technetium were decreased for the BSN test. For both BOH and BSN, there was a decreased removal of technetium and iodine in the synthetic perched water, which has higher concentrations of nitrate, sulfate, and carbonate compared to the synthetic groundwater. This work has been conducted with the Hanford site in mind. The testing our team has conducted is particularly relevant to the 200 West area within the Central Plateau at Hanford. This is a map of Hanford. The Central Plateau is here in the center, and we are specifically looking at the 200 West area, just this red and brown area here. The previous slide showed results from testing in various synthetic waters representing different geochemical conditions found in this area of Hanford. We've also tested multiple contaminants, uranium, technetium, chromium, and iodine, individually as well as combined, as the contaminant plumes can and do overlap in several locations. What I'll be talking about today takes the complexity one step further, adding in sediment from this 200 West area of the Hanford site to find out how these bismuth materials would perform in the presence of sediment. The sediment came from the Ringgold Formation and contained high amounts of quartz, feldspar, and calcite with lesser amounts of mica, chlorite, and amphibole, as shown here in the QXRD results. For these batch experiments, we used a 200 West synthetic groundwater with the recipe shown here. 0.5 grams of BOH or BSN was added to 100 milliliters of the synthetic groundwater with 10 grams of sediment. The target contaminant concentrations are shown here and were chosen to represent the highest concentration expected in the 200 West area of the Hanford site. For technetium and iodine, those values were increased by an order of magnitude because the detection limit of our analytical instruments would make it difficult to detect any changes if we use the lower concentrations. The batch experiments were left on a shaker except during sampling events, which occurred at 24 hours, 30 days, and 60 days. I'll be presenting results for the contaminants one at a time to discuss the effect of adding sediment into the batch system on each of the contaminants, starting with uranium. We have the time along the x-axis with sampling points at 24 hours, 30 days, and 60 days. The contaminant concentration is on the y-axis, represented in micrograms per liter, and the colored and dashed lines are pairs with the bismuth material with sediment, represented by solid lines, and the bismuth material with no sediment, represented by dashed lines. BOH is shown in blue, BSN is shown in green. The black solid line shows a control with sediment only, no bismuth material, and the dashed black line represents the contaminants by synthetic groundwater, so this is our initial concentration. As you can see, with only sediment, about 30% of the uranium was removed from solution. The BOH in blue removed the uranium to below instrument detection limits, with or without sediment present, but the BSN was only able to do that with the sediment present. The dashed green line shows that without sediment, the BSN only removed a small portion of the uranium by the end of the 60-day experiment. To explain this result, we have to look at the speciation of uranium in the system. The speciation of the aqueous uranium is controlled by the pH, the carbonate content, and the concentration of calcium and magnesium. In the synthetic groundwater without any sediment present, the carbonate to uranium ratio is the main factor controlling speciation and depends on the concentration of uranium in the system. As uranyl carbonate complexes form, the pH is lowered, so the speciation continues to change as the pH is changing. When the BOH or the BSN is added to the system, the pH is lowered even further due to hydrolysis of these bismuth materials. For BOH, the pH dropped to around 5.9. At this pH, there is a high uptake of uranyl carbonate complexes by the bismuth material. For BSN, however, the pH is much lower, as the BSN hydrolysis is only partially completed during the synthesis process. At a pH of about 2.4, there is little to no uptake of the uranium, as it's likely present as a cationic or a neutral species at this pH. When sediment is added to the system, the pH is buffered to around 7.6 or 7.8. Adding in the BOH or the BSN has little effect on the pH once the sediment is present, as the buffering capacity of the sediment is able to sustain the bismuth hydrolysis. At this pH, along with additional calcium and magnesium in the system due to dissolution of the minerals within the sediment, the speciation of uranium is primarily calcium and magnesium carbonate species, with a high uptake of these uranyl species by both the BOH and the BSN. Along with the calcium and magnesium carbonate dissolution, an increase in silicon concentration due to mineral dissolution could also lead to the formation of other phases such as uranophane. This figure shows the expected speciation of uranium in the 200 West synthetic groundwater. We did not include the sediment in the modeling, but wanted to use a simplified model to demonstrate the complex nature of the uranium speciation over a range of pH values, because these are all pH values that we can see in these different systems. The pH is shown along the x-axis and the concentration in micrograms per liter on the y-axis in log scale. This initial black line is showing the synthetic groundwater containing the contaminants with no bismuth materials and no sediment. With the BOH, the pH drops to 5.9. With the BSN, the pH will drop to about 2.4. When you add in the sediment, that pH with the BOH is going to stay around 7.8, and with the BSN is around 7.6. So you can see as we move through the pH in these different systems, the speciation of uranium changes quite a bit without that sediment present. Moving on to technetium, again we have the same test conditions with time shown on the x-axis and technetium concentration in micrograms per liter shown on the y-axis. With sediment shown with the solid black, blue, and green lines, lower concentrations of technetium were removed, and all or almost all of the removed technetium was released back into solution by the end of the experiment at 60 days. Without sediment, the BOH test removed most of the technetium from solution, shown by this blue dashed line, but the BSN did not, even in the absence of sediment. For both materials, the sediment had a negative effect on the technetium removal. Both BOH and BSN interact with technetium through outer sphere or diffusive layer adsorption and ion exchange for the charge balancing nitrate within the structure. This non-specific interaction means that technetium is more susceptible to release from the bismuth materials through ion exchange in the presence of other competing exchangeable anions in solution. Anions released from the sediment can also compete with the technetium for these exchange sites, and in addition, the presence of the sediment can physically restrict access to available exchange sites. For chromium, BOH and BSN remove chromium to below detection limits in all tests except for the final time point in the BSN test with no sediment. It is quite close to the detection limit though, which was 12.8 micrograms per liter. The detection limit represents removal of more than 72% of the initial chromium in solution. The efficient removal of chromium from solution, even in the presence of competing anions, indicates that it is likely removed through formation of inner sphere surface complexes between the chromium ions and reactive absorption sites on the bismuth materials. Results for the iodine show that the sediment alone removed 20 to 30% of the iodine, shown by this black line here in comparison to the initial concentration shown by the dashed black line. The presence of sediment did, however, have a negative effect on the removal of iodine by the BOH and the BSN. You can see that the dashed lines for BOH and BSN, representing the sediment-free tests, are below the solid blue and green lines showing the sediment tests for BOH and BSN. You can also see that some of the iodine that was initially removed at the 24-hour time point has been released back into solution by the 60-day time point. The mechanism for iodine removal is similar to that for chrome and involves specific interactions between the iodate ions and absorption sites on the BOH and the BSN. However, secondary mechanisms, including electron transfer from bismuth to iodate, resulting in some reduction to iodide and potential incorporation of iodide into neoformed bismuth phases, are important for the long-term retention of the iodine. The reduced efficiency of iodine removal in the presence of sediment suggests that competing ions such as carbonate released by the sediments inhibit the secondary mechanisms that are required for iodine retention in the solid phase over long periods of time. For the sake of time, I won't go into details on this graph, but in short, the elements are on the x-axis, and the circled x's are showing instances where the element is being taken up by the BSN in this case. BOH is not shown here, but had similar results. So along with the contaminants, you can see that there's also chloride and sulfate that are being taken up. Also in the BOH test, we saw that silicon was being removed by the BOH. These are the likely competitors that may have caused the decrease in the technetium and iodine removal, as these are all coming from the sediment as well as being present in the background solution, and may be causing the decrease in technetium and iodine removal. In conclusion, BSN and BOH can remove uranium, technetium, chromium, and iodine from synthetic groundwater solutions under various geochemical conditions. For BSN, removal of uranium improved in the presence of sediment due to pH buffering by the sediment, as well as dissolution of carbonates, leading to formation of uranyl carbonates. Chromium removal was unaffected by the presence of the sediment, but technetium and iodine removal was affected in the BOH and the BSN tests. This is likely due to competition with elements present in the background solution and elevated concentrations of these elements present due to sediment dissolution. We plan to continue this work with the next steps. We have planned our column tests conducted under continuous flow conditions, as well as using secondary treatments to prevent remobilization over time, like we saw with the iodine and technetium in the presence of sediment. Thank you for your time.